right, now that we are thoroughly practiced in solving all sorts of linear equations, both single variable and two variable or more systems of equations, we're going to start looking at what it really means to be linear, so the different characteristics in a linear equation. So let's go.
In this first lesson of Unit 2C, we are going to be focusing mainly on domain and range, but there's some other sort of elements to it that we're going to have to discuss as well, so it's going to feel a little bit like a hodgepodge, but it's an introductory to all the different characteristics that we're going to be looking at of linear functions. Before we get started, we're going to look at a couple vocabulary words for you to put in your glossary. So go ahead and pause the video, get these definitions copied down in your glossary. Okay, so you should have these all copied down. I'm just going to talk really briefly about them. Continuous and discrete are kind of opposites of each other. A continuous, usually we refer to them as different types of functions. A continuous function is a function that has no break in it. The domain goes over a whole set of numbers and there's no gaps anywhere. So it's going to be a situation where you can plug in any number you want and it'll be perfectly fine. Whereas a discrete is more something that is disconnected. So it'll be a situation where you're only looking at multiples of 5, or you're only looking at whole numbers, no fractions or decimals or anything. And there's lots of situations in real life situations that end up being discrete. So we'll look at some examples of those throughout this unit. Domain is the set of x coordinates. We're going to talk some more about that in the notes. Range is the set of outputs or y coordinates. We're going to talk some more about that as well. Interval notation is a way of writing sets of numbers, and we're going to talk a lot about that today as well. So we'll get into that momentarily. So let's go ahead and start our notes. The relationship between two quantities can be shown by a set of ordered pairs, and this is called a relation in mathematics. So pretty much anytime you're comparing two sets of data or two sets of numbers, it's going to be a relation. In a relation, the domain is the set of first coordinates. It's also referred to as your x values. You'll hear it referred to as the input. You'll hear it referred to as the independent variable. There's lots of different ways that the domain is discussed, so you need to know all of those words, and we've got a chart later in your notes that has all that information. The range is the set of second coordinates, or the y values. This can also be referred to as the output. It can be referred to as the dependent variable, but they are our y values. So, for example, if you're given a set of ordered pairs like this, your domain is going to be the set of first coordinates, so your x values. So my domain is -1, 2, 0, and -7. Usually we write that with a pretty set of brackets, which I am horrible at drawing. You know what? In fact, I should probably just type it because I'm really, really bad at drawing those. So let's just type those. So my domain is going to be -1 because I have that -1 there. It's going to be 2, and then 0, and then -7. So just one of each of these. Now, if oftentimes you'll see them written in ascending order, meaning smallest to largest, but it's not wrong if you just write it in the order you see it. There's no difference there. All right, our range then is going to be the y values, or the set of second coordinates. So when I look there, I've got the 4, I've got 6, I've got a -4, and I've got a 10. So when I type that up, we can go ahead and put it from smallest to largest. So that's going to be -4 is my smallest range, and then 4, and then 6, and then 10. So all we did was list out the numbers that show up in our y value. And again, if you don't want to put them in smallest to largest, it's not a big deal. Sometimes you might see things show up in different formats. We represent them as ordered pairs. This image right here is what we call a mapping. So when you have a set of numbers and it's showing how those numbers map to a different output. This is going to be your domain, the start of your mapping. So this is your input and this is your output because the arrows are going out to these. So your domain this time is going to be 2, 3, 4, and 5, just the numbers you see listed there. Your range then is going to be your output, which is right here. So when I list those, it's going to be -3, -2, 5, 7, and 9. Now, I do want to tell you that if you were to translate this to an ordered pair, so let me write this. If you were to translate this to an ordered pair, this would be 2, -2. So each arrow would represent an ordered pair. This one would be 3, -3, and there would be a second one with 3 where we go 3 and then 5. And then we go 4, 7, and 5, 9. So that's kind of how you read those mappings when you see them. Okay. We have a couple of different notations that that we use when we're talking about functions. The first is called set notation, and it uses inequality symbols like less than, greater than, less than equal to, and greater than or equal to. When a boundary or the edge of a line is included in your domain, we use either the less than or equal to or the greater than or equal to symbol, since the domain or range can be equal to that boundary. It's kind of the same as using closed circles as opposed to open circles when you're looking at graphing an inequality, or if you're looking at graphing a line that's an inequality, it's your solid line as opposed to your dotted line. Thinking back to previous units that we've done. If the boundary is not included, previously we would have used an open circle for that or a dotted line for that. When we're looking at set notation, that's your less than or your greater than without the equal to symbol. So when it is important to know that if your domain or range goes to infinity, then or negative infinity, then you use the less than or the greater than. That's because you never actually equal infinity, so it's not going to be less than or equal to. Another notation that we use to describe a set of numbers, and in this lesson to describe domain and range, is called interval notation. When we're working with interval notation, we use parentheses and brackets instead of inequality symbols. So we're going to use brackets when the boundary is included. So that's going to be in place of your less than or equal to, and in place of your greater than or equal to. If the boundary is not included, that's when we use parentheses. So you're always going to use parentheses if your boundary is infinity or negative infinity, again, because you're never actually going to get to infinity. It's just an idea that we aspire to, and you never actually get to negative infinity. So set notation looks just at the boundaries on the interval. So for example, if you have this interval, which is written right now in set notation, 3 is less than or equal to x, which is less than 7. Remember that equal to means that that 3 is included in the set. 7 does not have the equal to, so it's not going to be included. If I were going to write that in interval notation, I would write a bracket for 3 and then a parentheses for 7. And anybody looking at that would know that you're talking about a set of numbers that starts at 3 and includes that 3, because we've got bracket, and it goes to 7, or goes right up to right before 7, but doesn't actually include it, which is what that parentheses tells us. This example, negative infinity is less than x, which is less than or equal to 9, would be written as parentheses negative infinity, again, because that negative infinity is not included. And it goes all the way to 9, and that's why we've got a bracket there at that 9. So let's get into some actual domain and range equations or graphs so that you can see what we mean by this. If you have a graph that looks like this, to find the domain, what you're going to do is look at your x values. So when I look at this, I say, well, my x starts at -3. I go up to my x-axis and say it starts at -3. And because there's not an open circle there, I assume there's a closed circle, which means -3 is included. It keeps going all the way until we get to 6, and we have this open circle at 6, which means I'm going to put parentheses at 6. If I was going to write that, and you can draw yourself a line down to the x-axis to see that that really does go until 6. If I were going to write that in our other notation, it would be -3 is less than or equal to x, which is less than, not y. -3 is less than or equal to x, which is less than 6, because it goes from -3, where we have a closed circle, to 6, where we have an open circle. Our range then, for this one, to find the range, remember we look at our y values. We start at the very bottom and look at where it starts on the y-axis. The y-axis, it starts at -3, again with a closed circle, so I'm going to have my bracket there, and it goes all the way up to right here at +6. And that's an open circle, so it's going to be open. If I were to write it in my other notation, it would look like this. We had -3 is less than or equal to y this time, because we're talking about our y values, and that is less than 6. So these just happen to be exactly the same. They're not always going to be exactly the same. So let's look at this one. For this one, I'm going to look at my domain first. Because this is a discrete function, meaning there are gaps here, it's not a nice pretty line with no breaks in it, I'm going to have to just list, I can't draw those. I'm just going to list my x values. So I start all the way over to the left, and I see I've got a -4. So I'm writing -4. I've got a -3 here. I've got a 0, a 3, and a 5. Oops, fancy squiggles. So that's my domain. I should have done that in red, but I just... This is an example of a relation that is discrete rather than continuous, because notice, whereas here we had a nice clean line with no breaks or gaps, this is just disjointed or discrete points all over. So to find our domain here, we're not going to be able to use interval. We're just going to have a list of x values and a list of y values. So I'm still going to look at where I lie on my x-axis to find my domain. So this is at the point -4. So when I start my list with my ugly little braces there, I've got -4, I've got a -3, I've got a 0 on the x-axis, I've got a 3, and this one is at 5. And that's my domain for that one. When I get my range, or my outputs, I'm going to do the same exact thing, but this time I'm looking at my y-axis. Notice that I have, so I'm starting at the bottom and working my way up. Notice that I have 2 points that are at -2. I'm not going to list -2 twice. That is a part of the range just one time. And then my next point is here at 1. Remember, you're looking in terms of the y-axis now, so that is at the point y is 1. I've got y is 3, and y is 4. So in this case, my domain is larger than my range, and that's okay. In this last one, the domain, remember, to find domain, we start at the left and work our way right. Because we have an arrow here, that means that the domain starts at -infinity. It never we can never actually get to the beginning of this line. So it starts at negative infinity. We put a less than, not an equal to, and it goes to positive infinity because it's going to keep going to the right forever and ever and ever. So it goes to positive infinity. If I were going to write that in the other notation, it would be negative infinity to positive infinity with parentheses. One other thing, when you see something like this, another way that we write that is we could say that it's the set of all real numbers. Basically, that means all the numbers you have yet to learn about, or that you have learned about so far, are represented in the domain of this line. The range is going to work very similarly. Remember, for range, we start at the bottom and work our way up on the y-axis. Well, I'm never going to get to the bottom because as this goes to the left, it's also going down and down and down forever. So the start is negative infinity, and it's going to go, my y value is going to keep going up forever and ever and ever, which means I'm going to positive infinity. So the range is also all real numbers. It's very, very important that you know that in a linear function that doesn't have any restrictions on it, so if it's just a normal linear function, the domain and range will always both be all real numbers. And one symbol that I haven't shown you yet that can be used to express that is this little R with an extra line behind it. So I just finished telling you that in a linear function, the domain and range is going to be all real numbers as long as it's unrestricted. But most of the time in real life application problems, it's actually going to be at least somewhat restricted. So to show you an example of that, we've got this made up problem here about a car loan. So a car loan can be modeled by the function 15,000 minus 500x, where x is the number of months after the purchase. And they want to know what's the reasonable domain and range of this function. So to help better explain this, I'm going to draw a sloppy little graph here, okay, where I've got my x-axis. X is the number of months. So my x-axis is going to be months, and y is going to be the amount owed on the loan. So your loan balance is going to be your y. My starting value, or my y-intercept, is 15,000. This is just a rough sketch just to get an idea of what we're looking at. This is a really good strategy for dealing with word problems when doesn't necessarily require you to do a graph, but you just need a picture to really understand what you're looking at. So this slope of 500, because it's minus 500, I'm assuming that means I am making a payment of $500 every month. And we want to know how many months it's going to be before we pay it off. So it's going to go down 500 over 1 each month until we get to the end. So this is what my loan balance is going to look like. Now, for the domain and range of this, my domain, in most of the other problems, we looked at domain first. And here, my domain definitely starts at 0. Even though this is a line, it's not going to infinity because my car isn't going to, the loan isn't going to go up to infinity. This starts when time is at 0. So it starts right here at 0. When it ends, that I don't know yet, and I'm going to have to do some calculations to get there. But let's go ahead and talk about range for a second, because that we can pretty much get from the graph. Because when I look at this graph, it's clear that the bottom of this is going to be when I owe $0, because I'm not going to keep going down forever and have a negative balance. I'm going to stop making payments once my balance is 0. So when I hit 0, I have a dot, not an arrow. The upper limit of my range is that 15,000. So in order to figure out this missing domain value, basically that means what's the end of this loan? What's the last month where I finally hit a 0 balance on my range? To figure that out, I'm going to make my y value, or my balance, equal to 0. So it's going to be 0 equals 15,000 minus 500x. And all I've got to do to figure out the upper limit of that domain is solve for the x. So I'm going to subtract 15,000 from both sides. That gives me negative 15,000 is equal to negative 500x. And when I divide by that negative 500, I get positive 30. So that means that the upper limit of my range is going to be 30. At the end of 30 months, I've got a zero balance. All right, guys, you do have some practice to go here and check your packet to see if you have an application. Thanks for sticking with me on this long video.